Hey guys, it's Miss Marfleck here. The last time we met, we did functions inverses, day 1. And that was also a day that we did take a short quiz. So you didn't have any practice yet with the functions inverses day 1, which means that today's homework assignment is going to be inclusive of day 1 and day 2. So if you haven't seen the video where we did inverses, make sure you go back to our last classwork assignment and definitely check that out before you get to this video. Now we're going to do a quick recall from the last video since your homework will be inclusive of some of these things. And in the last video, our goal was to solve for the inverses. Now we had a few different representations, and our first representation for a function or an inverse function was numerically. Now numerically also means just having the table of values. Now we start off with a regular function here, and there's that function inverse notation. And like in the last video, we talked about how you can find the inverse of a function by just switching the x and the y coordinates, and then once you switch those x and y values, now you have the inverse of the function. And that's what inverse means. It means reverse, undo, opposite. So that's where we have that switching action between the x and y value. After we did numerically, the next representation that we looked at for our function was algebraically. And algebraically means that we can have an equation like so, and our goal in the last lesson also was just to find the inverse. So my goal is to find the inverse of this equation here, and we're going to first start off by using the notation we're used to. Instead of having f of x, we're going to have y here. Now this is still the original function, and then just like in the table of values, once we switch the x and y, now I'm working with the inverse function. But once again, this is not a way that we're kind of used to seeing a function. So once you switch to x and y, to solve for the inverse function, you have to solve for that y. So I'm going to multiply here by 2. And then my goal is to continue isolating y, which means I'm going to subtract 4. And then I have to divide on through by -5. And then once we have this function down here now, we solve for it using our inverse method, so we know that this is the inverse function and we don't want it to get mixed up with the original. So what we did after here was really quickly take out that y and replace it with that inverse notation. And then now that shows me, okay, now that's the inverse function. All right, so we did numerically, algebraically, and then the last representation we did was graphically. And with the graphically, you guessed it, we graphed. And our example here is y equals square root of x plus 3. And I'm going to do this now in our other sheet. Now this is what we did last time. I do have one extra coordinate plane, so I'm just going to squeeze it in down here. Number 1, 2, 3, 4, 5. This one could be number 6. And we're going to graph this function and the inverse. I did the original table of values in this light blue here. So we picked x values and plugged them in. Now I do have a radical, so I can't plug in any values less than 0. So we just do 0, 1, and then I'd go to 2, but I want happy numbers here that I can do without a calculator, so we'll do 4 and 9. All right, and then I just plug it into the function here. I plug 0 in, I get square root of 0, 0. 0 plus 3 is 3. Square root of 1 is 1, plus 3 is 4. Square root of 4 is 2, plus 3 is 5. Square root of 9 is 3, plus 3 is 6. And then we can graph these points here. When x is 0, y is 3. When it's x is 1, we have y is 4. When x is 4, we have y is 5, and then when x is 9, we got y is 6, and then we know what our square root function looks like, and it just has that transformation there of up 3 units. And then now when we're solving for the inverse function, no need to do any algebra, just use a numerical, your knowledge of numerically, and go ahead and switch those x and y values. And now I can graph 3, 0, 4, 1, 5, 4, and then 6, 9. All right, and then you got to look at the shape and think about how it's reflected over that line y equals x. and, you know, kind of fill in that shape there. And then we're going to fill in that line where we reflect over the line y equals x. And then you could see, you know, every blue point has a pink point across from it from that line there. And then that's just kind of like a quick, you know, rundown of what we did the last time we met. And now we're going to be moving on, and we're going to be taking a look at not finding necessarily the inverse function, but verifying that two functions are inverses, and we call this by composition. Now we're going to start off with a definition, and I'm going to say that this is a lot of writing, but after we go through this definition, we really only have like, I think 4 examples, and then I'm done with this video. Okay, so this definition is very important. Make sure you have this down. Definition of inverse functions. So we're going to start off with this definition by letting f and g be two functions to start. So not a relation, they are functions. And they're functions with specific characteristics such that when we compose them, which means when I put g inside of f, I can get out x. And, okay, this is a key word here, not or. We'll come back to that in a minute. When I compose in the other direction, when I put f of x into g and I get out x, okay, so if these two conditions happen, then we can say g is the inverse of f, and f is the inverse of g. Now this composition looks a little weird. You know, I know there's a lot of parentheses here. When we get to a practice problem, I think it'll be a little bit more apparent. We'll use some color coding to help us out. But basically this definition is saying, well, when I put one function inside of the other where the x is, and I simplify, if I get out an x and I do it in the other direction and I get out an x, then they are inverse functions. Now, if one of these conditions don't work out, let's say I compose them and I get an x plus 2, or I get like a 3x or negative 5x, anything that's not x, then they're not inverse functions. And then we do have some other notation. So this is a definition from the pre-calc textbook, but I'll use this notation, but normally I like to use the composition notation. It's kind of like, how should I describe this? This little bubble here is like an operation, you know? It's like an addition or subtraction or multiplication or division. When you see that little bubble, it's an operation. The operation means compose the two functions. And we're going to see composing as this. And then, you know, I'll just write the notation we're used to seeing from the definition. This means put g inside of f. All right, that's one that's listed second. And then we can go in the other direction. I'll put f inside of g. And here I am, g of x, g of f of x. So that's one notation, and I just want to squeeze in one more. I'll switch to a different color here. You can also see our traditional inverse notation, but usually this is used once you already know that they're inverses of each other. So if I say, like, you know, the following two functions are inverses of each other, verify their inverses using composition, then you can use this notation because you know they are inverses of each other. When you're not sure whether or not they're inverses of each other, we do use the f and the g of x. All right, so once again, this is like really the only, you know, a lot of writing that you have throughout this video. So this is super important. I can't stress it enough. Make sure you have this down. All right, now we're going to move on to some examples, and we're only going to do 4 examples. Today is a short lesson. It'll be a little heavier emphasis on the homework since we had that 25-minute video from last time. But here we are. We're going to do some examples, and we're going to verify if the two functions are inverses. And I kind of wish I wrote these directions a little different because verify sometimes assumes that they already are inverses, and I'm putting if here, but what I'm basically asking is see if these two functions are inverses, and we're going to be using the composition. So you can see if two functions are inverses by taking one, switching the x and y, and seeing, you know, doing the simplifying we did in the last video, and seeing if it equals the second function. But we're going to use that composition because we just learned that, and that's what we're going to be practicing with. So I'm going to give us our two functions here. There's that f of x, and I'm going to put the f of x in pink, and I'm going to do the g of x here in blue. So this is the problem, all right? But I do want to denote between those two colors there. All right, so now I'm going to compose them together, and I'm going to see if we get out if we get out x. So now you could do them in either direction. You can either start with f of g of x or g of f of x. I usually start with the f first, so I'm going to do f of, and I'm going to put g of x in for wherever the x is for our f equation, which means I'm starting with my f, and instead of having x here, I now have my g of x. So instead of x, I have my g of x equation. And then I have the rest of my f of x. All right, so you can notice that this equation here is like 3x plus 2, but it's not x, it's our g of x. All right, and then now that we've composed, we're going to do some simplifying here, and I use the color coordinating to see that this is g of x, and then anything in pink is f of x, and now we're just switching to a different color because now we're going to do some simplifying. So you could do this two ways. You could distribute the 3 and have 3x minus 6, and then divide each one by 3, or I can see 3 over 3 just crosses out or is 1, and I'm left with x minus 2 plus 2. And then x minus 2 plus 2 is just x. Now you may be thinking, okay, Ms. Marflag, they're inverses, but no. Look back at that definition. It's not or, it's an and, which means I do need to check in the other direction, which means I'm going to be starting with my g of x equation, and wherever I have an x in my g of x, I'm putting in my f of x equation. So here we go. Now my g of x starts with an x, okay? And we have a minus 2 over 3, but that x is my f of x equation. All right, so make sure you got that down, putting in, denoting with the different colors, the two different functions. And then now I can simplify here. It's like having 3x plus 2 minus 2. Well, that's just 3x, and 3x over 3 is x. Okay, and then now I see that when I compose both directions, we get x in both ways. That means, yes, they are inverses of each other. All right, we're going to move on to another example. Here we are taking a look at number 2. Using a little bit different notation here. Maybe instead of an x, we have a different variable like an n. Okay, but the definition still holds true. When you compose them, you're really looking for your end result to be the n, just n. All right, you could see I ended the radical there with that little line. All right, you can start in either direction. I like to do the f first, so I'm going to do f, and then I'm going to be putting g of n inside of there, composing g of n into my f. So I'm going to start off with writing my f function, and then wherever I have an n, I have to take out that n, and I have to replace it with my g function. So I have 2 plus n minus 1 to the 5th power, and then I still got that plus, I got minus 2, and then I'm going to put the end radical there, and I got a plus 1 on the outside. I wish I didn't squish it in, but I did anyway. So this ends a radical right there. All right, now I can do some simplifying here, and this is, 5th root, and I have plus 2 minus 2 under the radical. So plus 2 minus 2 is just going to combine to 0, and I'm going to be left with this 5th root of n minus 1 to the 5th power plus 1. And then now 5th root to the 5th power, 5 divided by 5 is 1. So this is n minus 1 to the 1st power plus 1. N minus 1 plus 1 is n. And you may be thinking, oh, yay, they're inverses. Not quite yet. We do have to go ahead and compose in the other direction. So now I'm switching it around, and I'm being very careful, and I'm keeping really good track of this notation here and my different colors. So I'm starting now with my g equation, which is 2 plus parentheses n, and now I'm taking out the n and I'm putting in my f of n equation. The radical ends there. We got the plus 1 there. And then now this is the n, and I still have my minus 1, and I have to the 5th power. All right, so this can be really confusing. So take your time, you know, and then maybe also go double check. Okay, well, I have 2 plus 2 plus. N is now this equation. So I have this equation for n. And don't forget the -1. Oh, I got the -1 there, and then to the 5th power. Now I can do some simplifying here. I got 2 plus this quantity now. +1 -1 just combines to 0. And then, you know, 5th root and to the 5th power will quote unquote cancel out or combine to an index of 1. So this is going to be n minus 2 to the 1st power. Just like you'd have, you know, square root of x squared is just x. And then now you have a +2 and a -2, and you also have n here. So yes, this one also turned out to be inverses of each other. All right, we're going to be moving on to a new piece of paper. So make sure you have down, you can pause the video, number 1 and number 2. Please stick around. We got 2 more to go. And you guessed it, you know, we did 2 of them where, yes, they did turn out to be inverses. So I think you can see where this one's going. This one will probably be a no. And here we are, number 3. We're going to have f of x is 1/2 x plus 2. And then we'll do g of x in a different color to kind of help us. And we got 2x plus 4. All right, so now my goal is to compose, put one function inside of the other. I'm going to start off with f, and I'm going to be putting in my g of x for where all of my x's are for my f equation. So starting off with my f equation, I have 1/2, and instead of having x, I now have this g of x equation, which is 2x plus 4. And I do have to put this in parentheses because the whole x is being multiplied by 1/2, and now this is the whole x. So this whole thing needs to be multiplied by 1/2. And then I still have that +2. I can't forget that. I still have that +2 off to the end. And then now that I've done the substituting, I can go ahead and simplify, which means this 1/2 has to get distributed to both terms. Okay, well, 2x over 2 is just x. 4 over 2 is 2. And then here we are. When I simplify, I got x plus 4. And then right off the bat, we have a no. I did not get x when I simplify. So it's important here to note that when you're trying to figure out if they're inverses, you do have to do both directions to verify that both sides are x. But once you get one side doesn't work out, you don't have to do the other side, because I already didn't pass one of the conditions for it to be an inverse. So no matter what, the other side turns out to be an x or whatever it is, one side didn't work out, and that's enough for us to see that that is a no. All right, we got one more here, and this is the last one that we're doing, and we got f of x is -3 plus, and we got a fraction, 2/5 x. And then g of x is equal to 5 over 2x plus 15 over 2. All right, so we're going to start off with our f of x equation, and we're going to take out our x, and we're going to compose in our g of x, all right, verifying that they're inverses using composition, which means I start off with my f of x equation, and then wherever I have an x, I take it out and I put in my g of x expression or equation there. And then now we can go ahead, now that we've substituted, we're going to see when I simplify, is this equal to x? So I'm going to do some simplifying here. We have -3 plus, and this is going to be 10 over 10x, which is just x. This is going to be 30 over 10. 30 over 10 is 3. -3 plus a +3 is x. So we're feeling pretty good, but we do have to do that other direction, which means I'm going to start with my g of x equation, and I'm going to be substituting in f of x. All right, so starting with that g of x equation, we have 5 over 2, and then wherever we have x, we have -3 plus 2/5 x, and then we still, ooh, this should be a blue parentheses, we still have that plus 15 over 2 off to the end. All right, and then now we can do some simplifying here, see if we get x. We're going to have -15 over 2 when I multiply this in, and then not just to the first term, but also to that second term, where we're going to have 10 over 10x plus 15 over 2. And then hopefully we can see this is 1x, and then these combine to 0, and we're left with x. And this is another example of, yes, they are inverses of each other. All right, that's the only examples that I'm going to do. I think it's more than enough to kind of illustrate how to use composition to verify if they are inverses, but there's a few things I just want to say before we end this video. And first is that I'm noticing here that all of my examples only had x one time. And that if you do have x multiple times, you do have to replace it multiple times. So that's something to keep in mind. And then another thing here is that the only thing that makes this topic, I think, a little difficult is keeping track of what part of the function is f of x, what part of the function is g of x, making sure that you're substituting correctly. And then the other hard part is the algebraic rules. So really kind of take your time and remember some of your simpler algebraic rules, such as distributing. Okay, once again, this is part 2 of inverses. This is the last thing that we're going to do with our inverse functions. Make sure you take a look or have already watched that first video, because your homework today will be inclusive of the first video and also the second video with composition. All right, get started on your homework and then email me if you have any questions.